Hello and welcome to this course on MATLAB programming for numerical computations. We are in week 11 of this course. In this week, we are discussing partial differential equations. In the previous video, we talked about using method of lines to solve parabolic partial differential equations. In this video, we are going to talk about method of lines to solve hyperbolic PDEs and first order PDEs. Okay. So, let us take a standard example. The standard example for first order transient model is shown over here. So, you have theta that depends on time as well as on location. So, let us say we have this overall domain, okay, and the things vary in z direction as well as they vary with time. Okay. At the inlet or at z equal to 0, we have theta in that is given to us. Okay. So, we need one condition for theta at z equal to 0, we need one condition of theta at time t equal to 0. Okay. So, what do we have? We have this particular domain in which theta is equal to 1 at one end, okay, and because of various processes that are described by the PDE, the theta will keep decreasing as the time progresses, as the length progresses. Okay. Initially, we will assume that there is no theta in this overall domain. So, initially we are going to assume theta at time t equal to 0 is going to be equal to 0 in the entire domain. What we are going to do is we are going to discretize this entire domain in n intervals. Okay, exactly as we have done before. Okay, and we are going to get this as location 1, location 2, location 3, so on up to location n and location n plus 1 as we have consistently done before. Okay. Our step size h of course is L divided by n. Okay. So, that is the overall setup for our problem. So, how do we do this particular problem is using method of lines. Now, before going on to method of lines, let us look at what happens at steady state. At steady state, d theta by dt is going to be equal to 0. As a result, you will get u d theta by dz equal to minus k theta, okay, and when you take u onto the other side, you will get d theta by dz is minus k by u multiplied by theta. You know how to solve this particular equation, and if you are able to solve this equation, theta at any location z at steady state is given by theta equal to theta in multiplied by e to the power minus kz by u. So, that is the steady state solution. We will use this later on to actually see how good our results are gonna be. Okay. So, now let us talk about how to solve using method of lines. As I said couple of minutes earlier, we have this entire domain. Okay. We have location 1, location 2, location 3 and so on up to n plus 1. Okay. At location 1, theta 1 is given by an actual value that is equal to 1, that was our inlet condition. At all the other interior locations, we will have to use our overall model in order to calculate the solution. Okay. So, this is going to, we are going to discretize this into n intervals, and because we are discretizing this into n intervals, we are going to convert it not n minus 1, we will convert it into n ODEs. Why n ODEs? Because y goes from theta 2, theta 3 up to theta n plus 1. Okay. We can then use ODE 45 or ODE 15s to solve the n ODEs that are resulting from this particular method of lines based solution. Okay. So, what are the potential approaches for using method of lines? Okay. The first one is, as we had done in the previous video, let us try using central difference formula for d theta by dz. If you use central difference formula at any location I, okay, this is going to be our central difference formula. So now if we substitute this central difference formula into our overall equation, we are going to get d theta I by dt equal to negative u theta I plus 1 minus theta I minus 1 divided by 2h minus k times theta I. We have done this multiple times, so we do know how to do this. So, I hope this particular process is clear to you by now. So, our solution vector is y. Let us also think about our what theta is going to be. Theta is going to be nothing but theta 1, and this is up to n plus 1, not n. Theta 1, theta 2, theta 3 and so on up to theta n plus 1. Okay. This is nothing but y. Okay. So, therefore, our capital theta is going to be nothing but theta n by y. Okay. Again, this particular step is not necessary, okay, but we will use this step so as to simplify our way of solving. Now, let us look at what's going to happen. Okay. At this particular location, location 2, we are going to use the values of theta 1, theta 2, theta 3, and we have those values in our theta vector. For location 3, we are going to use the values theta 2, theta 3, theta 4, okay, and that is going to be fine. So on, we will go on until location n. Now, let us look at what happens at location n plus 1. Now, what happens at location n plus 1? If we were to use the central difference formula, we will have theta n plus 1 and theta n plus 2. Now, theta n plus 2 is not in our domain. Theta n plus 2 lies outside of the domain. So, how do we handle this particular situation? At the nth node, we are going to use a backward difference formula. We can either use a 3-point backward difference formula or a 2-point backward, the regular backward difference formula. In this particular example, I am just going to use a regular backward difference formula. So, at n plus 1, I am going to use d theta by dt equal to negative u theta n plus 1 minus theta n divided by h minus k theta n plus 1. That is what we are going to use. Okay. Okay, so let us go on to MATLAB and try to solve this problem. Let us discretize into 50 domains. You have h equal to L by n, your z goes from 0 to h to L. Okay, and let us say initial conditions and solution. What are our initial conditions? Our y naught is going to be zeros of size n comma 1. That is going to be our y naught. T span equal to 0, let us see what we had, 0, 0.5, 1 and 5. Okay. And we will have T sol ODE 45. PF for fun y comma. Okay, so this is how we are going to solve this. Okay, so let us also create the function y. Okay. So, this is the parameters, and okay. So, this is what we have. Okay. So, let us go over here and see what we had written. Okay. So, first what we had is we have defined our theta as theta in and y. So, let us do that. Theta is going to be theta in followed by y, where y is our solution vector. Okay. Let us define the theta equal to zeros n plus 1 comma 1. Okay. So, just the way we have theta, it will just be convenient for us to define the theta by dt also, and we will ignore the first element. Why we will ignore the first element? Because theta in is given to us, theta 1 is given to us, so we are not really interested in that. Okay. And at the end of everything, we will have for I equal to 2 to n end, and finally we will have dy is nothing but d theta 2 to end. Okay. Now, why? Again, because y is nothing but, you leave the first element, so from second element right up to the n plus 1th element is our y. Likewise, dy is also going to be from second element to the last element. Okay. So, that is why I have our theta equal to 2 to our dy equal to d theta 2 to end. So, that is what I have, and let us actually put the model equations. Okay. Yeah. So, for I equal to 2 to n, the theta I is going to be equal to, what do we have? D theta I is minus u multiplied by theta I plus 1 minus theta I minus 1 divided by 2 into h. Remember to put the brackets around 2 into h, minus k into theta I. Okay. So, this goes from 2 to n, and for at n plus 1, what we need is the theta I is going to be the backward difference formula minus u multiplied by theta n plus 1 minus theta n divided by h minus k into theta n plus 1, right. So, yeah, I think that should be it. Okay. Oh, we need to define h, right. So, length was 1, and we will have to define n also, n equal to length of y. Okay. So, y is size n vector, right. We have defined this y as a size n vector. Why? Because it goes from 2 to n plus 1. So, our n is just equal to length of y, L is equal to 1, h equal to L by n. Now, what we will also do is we will plot this. So, let us talk about plotting. Plot h to L, that is our z values, and y sol. Okay, so that's what we are going to do. Okay. Now, what I'm trying to show over here is for a problem of hyperbolic PDEs or for the first order PDEs, which are basically initial value problems in Z domain. Okay. For those type of problems, our central difference formula does not work. I will try to demonstrate why the central difference formula does not work, and then I will talk about what are the alternative approaches. So, let us now run this code and see what happens. Hopefully, it will not give any errors, but we will see. Okay. Yeah, the code has run and this is the overall result. Okay. So, this is at t equal to 0, this is at t equal to 0.5 is the red line, t equal to 1.0 is the black line, and t equal to 5.0 is the green line. Okay. What's happening over here is we are getting a non-physical solution. Okay. Now, this is what is known as a advective type of a problem. Okay. So, this is a little bit of an advanced idea. So, what happens? So, for example, what do we mean by that? The type of problems that are defined by these type of PDEs is where you have something that is moving from one side to another and it is disappearing because of certain processes. Okay. As a result, the overall solution is going to be monotonic. It can be monotonic decreasing or it can be monotonic increasing. It cannot fluctuate the way you are seeing in the red and the black curves. The reason why it fluctuates is because our central difference formula for hyperbolic PDE is not a stable method. Okay. This is something that I am not going to cover the theory behind this, because that will probably take an entire 1 hour lecture. Okay. But it is a very well established theory that for first order PDEs, the central difference formula applied naively without close thinking does not give a stable solution. Okay. So, this particular example exactly demonstrate that behavior, is that you do not get stable behavior if you use central difference formula for solving a first order PDEs. Okay. So, if we were to use backward difference formula, what is going to happen is our d theta by dz is just going to be at location I Okay. As a result of this, the differential equation in time, we are going to get d theta I by dt equal to negative u theta I minus theta I minus 1 divided by h minus k theta I. If we go to the previous slide, this is exactly what we had gotten for the backward difference formula at the end point, right. So, this particular equation for backward difference formula method of lines is going to be applicable for the entire range of I, that is for I equal to 2 to n plus 1. Okay. As we had done in the previous example, we are going to define theta as nothing but okay. So, let us go on to MATLAB and modify the previous file. Okay. That is all we really need to do, is to modify the previous file. So, let me close this and let me say save as. Okay. Okay, so we just saved it as small PFR BKD, and let me open this. Okay, using backward difference, discretization part, all of this remains the same, initial condition and solution remain the same. Okay, PFR fun, we will call it BKD, and this also PFR fun BKD. Okay, the parameters remain the same, our calculation of n and h remains the same, the definition of theta vectors remain the same. What is going to happen is this, we are going to go up to from I equal to 2 to n plus 1. Okay, and we will delete this, and instead let us use this to find out how to solve, how to use. Okay, so we are going to have the theta I is going to be equal to minus u into theta I minus theta I minus 1 divided by h minus k into theta I. Okay, so this is what we are going to get, where we just replace I with n plus 1, we will find d theta n plus 1 is going to be minus u into theta n plus 1 minus theta n divided by h minus k multiplied by theta n plus 1. All the time you replace I with n plus 1 and you will see that the second equation becomes exactly equal to the first equation. Of course, we do not need this equation and we will delete this, and that is all. So, literally what we have done is we have removed the d theta for location n plus 1 and for location 2 to for location I equal to 2 to n plus 1, for that entire set of locations what we did was we replaced minus u multiplied by theta I minus I plus 1 minus theta I divided by h minus k into theta I. That particular guy we replaced it with the backward difference formula. That is the only change we have done. As you have seen, there is no other change that we have done in this particular example. Okay. So, now let us save this and run it and see what we get. Okay, hopefully it will run without an error. So, let us see. Okay, and indeed it has run without an error, and as you can see, this is the more physically correct solution. Okay. So, as time progresses, your theta values start from 0, they increase, okay, and then they again decrease. So, this is how this overall process of getting the solution works. Okay. Now, what we will do finally is we will compare it with the steady state solution. What was the steady state solution? Theta equal to theta n multiplied by e to the power minus kz by u. Okay. So, we will say theta steady state equal to, so theta in was just 1, so 1 multiplied by exp minus k into z divided by u. So, minus k into z divided by u, and u is okay. Let us actually evaluate selection in command window, so that we have these values. Okay. Yeah, that I think should work, kz by u. Okay. So, let us say hold on, plot z comma theta SS magenta color dots is what we will plot this as. Okay. And this is our steady state solution. So, as you can see, because this is first order accurate, the backward difference formula is first order accurate. Therefore, even when we have n equal to 50, so as many as 50 nodes is how we have discretized. Even in a situation like this, you can clearly see there is a small amount of error between the steady state solution obtained using hand solving versus the transient solution that we obtained using method of lines. Okay, so let us get back and see what we have done in this particular video. So, what we did was we tried to solve the partial differential equation using method of lines. We started off with the central difference formula for the method of lines. However, the central difference formula we saw does not give the correct solution. It does not give correct solution because for first order and for hyperbolic PDEs, the central difference formula is not stable. Then we said that we will go on to the backward difference formula, and when we use backward difference formula, indeed we found that the overall solution was stable. But because the backward difference formula is first order accurate, we needed to use a large number of nodes in order to get a reasonable accuracy. Even with using as many as 50 nodes, you observed that the accuracy was not very great. You could actually see a very small difference between the magenta dotted lines from the analytical solution and the solid lines from the numerical solution. Okay. So, that is what we have done in this particular video. I hope between the previous video and this video, we have covered some of the most important way of solving transient PDEs, which is using the method of lines. With that, I come to the end of this video and I will see you in the next video. Thanks and bye.